In this talk, I will describe what I found and what I learned about functional programming while I've been writing a book about it. First of all, about myself, I have an education in theoretical physics, and I used to write papers on physics that looked like this. Eventually, I repented and turned to software engineering. I've been studying functional programming since 2008, starting with languages OCaml, Haskell, and finally Scala. I've been learning from reading papers, reading online tutorials, books, and attending the Scala by the Bay conference, which I've been attending every year since 2014 in San Francisco. Since 2015, I'm using Scala professionally. So why did I decide to write a book about functional programming? This is primarily because I found that the functional programming community is very much different from other programmers' communities. Other communities, say Java, Python, JavaScript, focus on their language and on their libraries and frameworks, how to use those libraries, and occasionally how to design new libraries. And the things they talk about is, here is how you configure, this method needs to be overridden, put this annotation, and so on. So how to use specific features of those frameworks and what benefits they give. The functional programming community sounds very differently. They talk in a different way. They talk about referential transparency and how that is good for your code, algebraic data types, and monoid laws, and parametric polymorphism, and free applicative functors, and monad transformers, and so on, and catamorphisms. You can just go to YouTube or Google to find presentations about each of these things, and these presentations will be given by programmers. I don't think you can find dogomorphism, but catamorphism certainly. John de Goos has put together a glossary of more than 100 functional programming terms like these. Eventually, I realized, going to the Scala by the Bay conference, that each year more and more the Scala community has embraced these concepts. More and more of these talks appeared, and finally in 2018 one of the talks had this title, The Functor Applicative Monad Talk, implying that everyone expects to hear these things at least once, so why don't I give a talk about that? So that was by 2018, and here is an example of a quite obscure error message in Scala where it tells you that some type is not correctly matched, and this is a GADT Scala. Now what that means is actually quite difficult to understand. So this was a very intriguing thing for me. So why do these programmers, they're not academic scientists, they're programmers, why do they talk about those things? And no other programmers seem to do so. So I decided to learn this, and my main questions were, first of all, what knowledge will actually help me write Scala code? For example, do I need to learn what that means, GADT Scala? Or do I need to learn the workaround for this particular error and why the Scala compiler didn't like the code and how to make it compile, without actually learning the theory behind these words? Maybe that's the case, that I have to learn that theory, but that was my question. So what is the scope of the knowledge of theory that actually helps me write code? And where can I learn about that? I would like to have definitions, clear definitions, and examples of code. For instance, what is a free applicative functor? What is the definition of that? And how do I implement the code for this? How do I make sure that I implemented it correctly? And so on. That is what I was looking for. I was not looking for theory for the sake of theory that has no specific applications and no benefits to programmers. So for instance, there is a joke in the community: a monad is just a monoid in the category of endofunctors. What's the problem? Now the joke is that actually it is true, technically speaking, about the monad, but it is useless for programmers, and so understanding why this is so will not help you write code, and this explanation certainly does not help to understand what a monad is and how to use it. So I was not looking for such theory. I was not looking necessarily to learn why that is true unless it helps me write code, and I don't believe that is the case for this. Another example is from a category theory blog by Bartosz Milewski. One of his chapters, for instance, is about low-veer theories as an alternative to monads. Now, it is a purely academic question at this point. There are no applications. It's not clear if it's really an alternative to monads or not. And so that is not something I wanted really to learn about. So I kind of looked at it and skipped it. There is recently a published book called The Book of Monads, which I very much looked forward to. It kind of appeared too late for me, but still. There are some parts in this book that are theory for the sake of theory. And one part is that explains monads from disjunctions. It's towards the end of the book, but that construction is never actually used in practice, and I do not believe it is useful. So, but at that time I did not know. So how do I choose what I have to learn? Do I have to learn disjunctions? Do I have to learn what is endofunctor? I was also not looking for heuristic explanations without proofs. That is the case of most functional programming books today. They do not have any proofs. They do not give any rigorous definitions, or very few. There are a couple of books like this one, Introduction to Haskell, and this one. This is a book that I read when I first learned Scala. Some of these books include a few proofs, and these are only the simplest proofs. The Book of Monads, I believe, does not actually include any proofs of any laws of monads at all. So I was interested in finding proofs because I would like to verify that some things are correct about monads, or that my code is correct, but I could not find books that show those proofs, or it will be extremely academic and not really practical. So as an example, the Book of Monads tells you about different monads, such as reader, writer, state, continuation, and so on, but it does not actually prove that those are correct monads, that they satisfy the laws of the monads. I was looking for that and I could not find it. So I kept reading different materials, papers, and I got more questions than answers. So here's, for example, what you can read about monads. Often monads are not defined in terms of unit and star, but rather in terms of unit, join, and map. 3 monad laws are replaced by the first 7 of the 8 laws. I'm lost already. I have no idea what that all means. How do I define star and follow? How do I get the other laws? How do I derive? It's not shown in this paper. It's not indicated, and there's no tutorial that tells me how to do that. Wikipedia is not clear. A monad is an abstraction that allows structuring programs generically. What does that mean? Category theory provides monad laws which will be satisfied and can be used to verify monadic code. What is monadic code? How do we verify it? It's not clear. I can't understand this. The book Functional Programming in Scala also is a very good book. There are, however, some things in it that are not clear and not sufficiently explained. Here's an exercise about applicative functors. Show that this formulation is equivalent in expressiveness. I don't even know what that means. What is expressiveness? In which units do I measure expressiveness so that I can see that one thing is equivalent in expressiveness to another thing? I don't know that. So I don't really understand what I'm supposed to do. I wrote some code. Is that enough? If I define something in terms of apply and unit, is that enough? I don't know. So Wikipedia is also not helpful. Applicative functor is an intermediate structure between functors and monad. What does that mean, intermediate structure? It is a functor or not? Is it a monad or not? It is a functor but not a monad, but maybe it is a monad. For instance, list is a monad and it's also applicative functor. And option is a monad and also an applicative functor. So in what sense is this intermediate? And that kind of thing is just completely abstract and doesn't help. So can't really understand that. FreeMonads is another fascinating topic. The return and flat map constructors witness that this data type is a monad. Now, why is that? Is that because some case classes is called flat map? That's what makes it into a monad, because it's called flat map? What if I called it XYZ? It wouldn't be a monad anymore? Confused. I'm confused. They are exactly the operations required to generate a monad. We say that it is a free monad. What does it mean, free monad? Why is that? Wikipedia is not clear. Can't really understand. So I kept getting these questions and kept reading. Found that most resources are either too academic or too practical, too close to practice. They do not give me what I need. Haskell Wikibooks is one resource that is at the right level, but it doesn't have enough definitions and proofs and derivations. It doesn't show why this is all true. Functional programming in Scala has a few derivations, but doesn't explain enough. So that's why I wrote a book about this. I could not find a book that gave me what I wanted, the answers to my questions. What I found is that I could systematically determine which parts of theory are relevant to practice. I will explain how I did this. I found also an interesting way of systematically organizing this knowledge about FP, functor, monad, applicative, and so on. This is not just random. So there's a systematic way of looking at it, which tells you at the same time what is practically relevant. And finally, I found ways of verifying all these statements through rigorous derivations. So if I claim that something is a monad, I verify by derivation that this is so. This is a new approach that I don't think any book follows right now. So it looked to me an interesting project to write it up as a book. So I started about 3 years ago doing YouTube videos on these topics, and then later started writing up a book. So this book explains the theory and applications of all those major design patterns of functional programs. So functor, monad, applicative, and so on, they're really design patterns. And techniques for deriving and verifying their properties need to be developed. They're not obvious, they're not very easy, So you need to learn at least how to formulate those laws and properties of types. And I give practical motivations and applications of all of these techniques to Scala code. So now, what did I learn after this experience? I've been working on this book for almost 3 years now. The book is close to being complete, and I can formulate what I have learned. So the first and most important thing I learned is that functional programming is an area of programming, or a paradigm of programming, where programmers find certain questions about code that have rigorous answers. Answers that are not a matter of opinion, not a matter of experience. So if I say blah is a monad and somebody else says no, it's not a monad, that question can be decided by mathematical derivation. It's not my opinion versus their opinion. Moreover, the answers to these questions will guide the programmer in writing the code, in designing the software. It is not just an academic question. It is not just a question about verifying the code after it has been written. No, this is a question about how to write the code. Do I use this type or not? Should I modify this type, this data structure? Because it's not a monad, I need it to be a monad. And like I will show, there are certain data structures that are not monads, others are monads. These are the kind of questions that only functional programming allows us to ask and answer rigorously. Here are the examples of these questions. Imagine you have a Scala type of this sort, so either of z and the function r to a, and another type is r, function from r to either of za. So are these types equivalent? Or can we have a function, say f, that takes a value of the first type and give me, or the second type, gives me the value of the first type, and vice versa, takes some value of the first type and gives me some value of the second type. So can I implement these functions? So it turns out we can implement the g, and there's only one way of really implementing it. You need to take this r, and you need to insert it into here. If there is an either on the left, and you just keep that. So there's an either of z returned, and otherwise you return either of right of a. So that is the code that you can write, and there's essentially only one way of implementing this function. And it turns out that the function f cannot be implemented at all. It's completely baffling that you can even ask and answer such questions. So you have a type signature of a function, and you find out that you cannot implement that type signature. Something is wrong with that type signature, that it cannot be implemented. And this is a rigorous result. You don't need to write tests to check this. And actually, there's a theory that explains what can be implemented and what cannot be implemented in this kind of function. Programmers need to develop intuition about this so that they don't write APIs with type signatures that cannot be implemented, although they look like they would be useful to implement. The programmer needs to understand why you cannot implement the function f. So, for example, here, you're given this, and you're supposed to return either z or this function. So you have to develop intuition about what you have to do to implement this function. And in this case, what you need to do is you need to return this either left or right. And you have to decide which one you return before you evaluate any function, because on the left you have a function and it needs an argument of type r, but you don't have a value of type r. First, you need to decide if you're returning left or right here. So if you decided to return left, then you're supposed to produce a z, but you can't produce a z, you don't have an r. And if you decide to return the right, then you can have an r, and then you can get either z or a, so you're not guaranteed to get an a, but you're required to return it. And it will be too late at this point to decide to return left of z, because you already decided that you will return right of this. So this is the kind of heuristic explanation of why you cannot implement this function. But this result is rigorous, and the theory that you can study, and there's an algorithm that you can study to show you how to answer these questions. A second example of reasoning task is that suppose you have code where you want to combine a future and an either in a single for yield structure. So you have a computation that is run asynchronously, you have another computation that could produce an error of a certain kind, and again a computation that can run asynchronously. So this certainly won't compile. So you need to replace these type constructors with something else, but with what? So should it be a combination of either and future of this kind, either of z future a, or should it be future of either za? So you're trying to combine either with future so that you can use flat map on that result. It turns out that this is wrong and this is right. Again, this is a rigorous result. This is not an opinion. This is not because of somebody's experience. This can be derived. This can be proved. Programmers certainly do not need to know these proofs, but they need to have intuition that at least there is some kind of proof and some kind of derivation that tells you what is right. There is actually a single answer, correct answer, and if you have this question, you know what to do. So you can study the theory of monad transformers and their laws if you want. You don't have to, but you need to know as a programmer that this thing exists, that this is actually objectively a wrong answer. You cannot implement flat map correctly for this type. Another example where you cannot implement flat map correctly is this type constructor. Very simple. And you want to write a flat map like this. And you can actually implement flat map. You can compute some kind of option of BBB, but it will fail the monad laws. It will always fail. Whatever you try to do, it will fail the monad laws. So this is a difficult example because it's not obvious why this is wrong. So this, you could be tempted to do this, but it would be wrong. What would be the consequence of using this flat map that violates the laws? The programmers need intuition about it. So what is wrong with this? And how should I modify this data structure so that I can implement flat map correctly for some modified data structure? Because imagine that your business logic dictates that you have this data structure, or at least that you have this data structure and maybe some more data, and you need to have a monad out of it. So again, this is a rigorous result. This cannot be disputed. There's a derivation using the theory of the laws of monads, where you prove that this cannot satisfy laws. Final example is with the FreeMoon. There are three different talks that I found that explain the FreeMoon, and neither of them have a rigorous definition of what the FreeMonad is, and they have three different implementations, the different case classes, and so that's confusing. So why are they different? Are they equivalent or not? And is one of them not really the free monad, or what? What it turns out to be is that there are more detail that needs to be specified when you talk about a free monad. So you can have a free monad on a functor, or you can have a free monad on a non-functor. You can have a free monad that assumes the monad laws in its construction, and that would be less code, fewer case classes, than a free monad that does not assume laws. And there are performance implications of doing this. You can define a free monad really in different ways for different cases. So these are rigorous results. Other than this, the free monad implementations are equivalent to each other. You can prove that they're equivalent. And there's a theory of how to implement free inductive type classes. Free functor, free applicative, free contravariant functor, whatever other inductive type class you have. And if you study this theory, you will know how to do this in different cases. And that's what you could study. Or you could just look at some of these examples, get intuition, but you need to know that there is a theory, that there is a proof to be made. For example, the equivalence of types between what is defined here and what is defined here in case of a free monad on a functor. So those are equivalent, and you can prove that. And for instance, the programmer could then answer another question about a free monad, like this question. How do you define a free monad on a pointed functor? So you have a type constructor that is already a functor, and already it has a pure method as well. So it has a map and pure. It just doesn't have flat map or flatten. So how do you define a free monad for that? And there's a procedure and a theory, and if you study that, then you would be able to do some derivation and come up with the correct code. So functional programming is the only paradigm that I know that allows programmers to ask and rigorously answer questions of this kind. These questions are relevant to writing code. They're not about the business logic, not about the domain of subject matter. They're about writing code, the data structures in the code and their properties. So this aspect of functional programming makes it close to engineering rather than tradecraft, artisanship. If you just write code through experience, tradition, imitation, and best practices, that's artisanship. It's not necessarily bad, but it's a different kind of activity. A lot of code has been written for scientific computing, for data science, for things like aerospace control. All of these subject matter areas are highly mathematical and rigorous, but the code is not written in a rigorous way. The code is written by trial and error, through experience, and so on. It's an artisanal kind of code. So the business logic could be mathematically rigorous. Doesn't mean that you're doing software engineering as such. So then I realized that software engineering is a misnomer. We're not really engineers, although that's our job title. We are software artisans. We do not use engineering unless we use a method like functional programming that is based on derivations and mathematical science. So functional programming is similar to engineering in a number of ways. So let's quickly take a look at engineering. So mechanical engineering, electrical engineering, and chemical engineering are based on calculus, on classical mechanics, quantum mechanics, electrodynamics, and thermodynamics, and so on. And functional programming is based on category theory, type theory, and logic proof theory. So that's a big similarity, that the questions that engineers answer based on electrodynamics or mechanics are similar to questions that programmers answer based on category theory, like how do you implement a free monad? Engineers also use special terminology. So all those words that we use, that's similar in engineering. So here are some examples of what engineers use, the terminology. They use rank 4 tensors. They use Lagrangians with non-holonomic constraints. They use Fourier transform of the delta function. They use inverse Z transform. And they use Gibbs free energy. So compare this with rank n types, continuation passing transformation, polymorphic lambda functions, free monads, or hylomorphisms. So this special terminology is not self-explanatory, just like in engineering. What is a lambda function? What's lambda? Why am I supposed to understand what that means? I'm not. It's a special terminology that needs to be learned separately. A free monad, what does that mean? So just like free energy, it does not mean energy for free. This is a special term that has specific definition in thermodynamics. It's a function of certain arguments with certain properties. And the free monad is a special term. It's a certain data structure with certain properties. So that's very similar. If you look at books on mechanical, electrical, and chemical engineering design, then the books look like this. A lot of equations, a lot of diagrams, a lot of calculations. The books on software design and architecture look like this. Good class interfaces and consistent abstractions. Write good code and don't write bad code. That's what they tell you. So that is a big contrast. So they're not really engineering. They're artisanship. There are 2 books right now being written. My book is one, and there's another book by Oliveira, Program Design by Calculation. Those are the books that pursue this idea of applied science of functional programming. And they look similar. They have derivations, they have math, they have some diagrams, and not just code and text as the books on software engineering that we have now. So these are the differences. Functional programming makes programmers more like engineers. So now I turn to another topic, which is the science of map, filter, reduce. Map, filter, reduce programming style is a success story of functional programming. It gives a way of doing iteration and iterative computations, aggregations, and so on without writing loops. It's a very mathematical looking approach. It's functions applied to arguments, and the results are again applied to some arguments and so on. So it does not look at all like loops with statements inside. Here's an example of an easy interview problem that you might encounter. Say, compute the list of all integers between 1 and 100 that can be expressed as a product of 2 other integers in exactly 4 different ways. So the solution of this is essentially a one-liner. And you just filter by a condition, which is obtained by counting how many times you can get something to divide n. So exactly 4 times, you're done. So this is the result. So this is the kind of power that comes with map, filter, reduce. A very essential part of map, filter, reduce style is nameless functions. Functions that have no names, that are just written like this, not separately defined, but written in line. They're called by different names, lambdas, closures, and they have been added to most programming languages by now because they are so useful that even very conservative programming languages like Java and C++ added them. The essential methods of this style are map, filter, flat map, zip, and fold. Very similar techniques work with parallel processing. Spark was the first major application that had extreme success. Stream processing is done in the same way. Even relational databases can be accessed in this style. It's a very powerful style of programming. Of course, I learned that very early encountering functional programming, as every programmer should, that you have these methods and you can do a lot of work with them. And then I started asking questions like, what are other data types that can have these methods? Because these are all sequence-based calculations. You take, say, a sequence and you zip it with another sequence, or take a filter of a sequence, you get another sequence. What about just plain algebraic data types? Can you define map, filter, and so on for them? What about trees? What about other recursive data types? Like this is an interesting data type, perfect shaped tree, which always has the same depth in all leaves. So it could be 2 leaves, 4 leaves, 8 leaves, and so on, but only those, no other shape. Must be a perfect shape. So this is an interesting data type. Can you define map, filter, flat map, zip, and fold for this? It turns out that you can define zip, for instance, but you cannot define flat map or filter. But anyway, that's just, again, this is a question that I had, and just let's take a look at another data type, like this one. It's a function from string to some stuff that expresses your business logic. Can I define zip for this with respect to the type parameter a? Can I define flat map for this? Can I define filter? Can I define something else? So I started to ask these questions, and I found that this gives me a systematic approach to understand functional programming. So first of all, I determine the laws that are required of these methods. The laws of map, filter, flat map, zip, and fold. These laws express the expectation and the intuition of programmers about code written using these methods. So for example, if you first filter and then map, this is equivalent to first mapping and filtering with something else. So that kind of expectations you can write down as equations and verify rigorously if they hold. You define then the corresponding type classes that have these methods satisfying these laws. And then the second thing that I realized is that you can build new data structures from old ones, preserving the type class laws. So here's an example. If P and Q are filterable functors, so they have map and filter, then either P of A, Q of A is again a filterable functor. So they have these methods. If P of A is a contravariant functor, then this function, understood as a type constructor with type parameter A, is a monad. Now this is not at all clear and obvious why that is so, but I looked systematically at all these constructions and found which one worked. For instance, if P of A is a monad, then either of A, P of A is also a monad. And if P of A, Q of A are applicative, then either P of A and the pair of A, Q of A is applicative. But without this A, just either P of Q will not necessarily be applicative. So I found many more type constructions of that sort, where I take one or two existing type constructors with known type class instances, and I can make new ones out of them. And sometimes it turns out it was necessary to define new type classes, like contravariant filterable and contravariant applicative. So this is my systematic approach, which I went through entirely in this way to develop intuition about how I can implement lawful methods of type classes. What data types can have those methods and what data types cannot have those methods? How can you spot problems, so to speak, that something cannot have a filter operation? What is missing? What needs to be added to have a filter operation on the data type? And I also developed special notation and proof techniques because a lot of this needs to be derived in a mathematical way. It's a lot of writing if you write Scala syntax for these things. So instead of Scala syntax or even Haskell syntax, it's still too much. I developed my own very short notation and techniques of proof. So while doing this, I realized that types play a central role in functional programming, in the sense that there are specific type constructions that play a role. Not just the existence of types, but there are specific constructions that are very important for functional programming today. And these are unit type, type parameter, product type, coproduct or disjunctive union, function type, and type recursion, a recursive type with a recursion scheme, which I will not talk about in detail, but this is very important as a construction. So functional programming today is not just programming with functions. It's programming with functions that have arguments and values of types made by these constructions. This is very important. A language should support these constructions. Then you can do good functional programming in it. And going through all of possible type combinations with these constructions, you can enumerate essentially all possible type class instances. You have to check that laws hold in each case, which is a lot of work. But once you have done this work, you have essentially all possible functors, filterable functors, monads, applicatives, traversables, and so on. And in some cases, you know how to generate the type class instance automatically. You can write a macro or a code generator in some cases. Just as an aside, unit, product, coproduct, and function types correspond to logical propositions. This is the Curry-Howard correspondence. The propositions true, A and B, A or B, if A then B. So logic that does not have some of these operations is incomplete. And not all programming languages support all of these type constructions. So, for example, the Go language does not support coproducts. Actually, a lot of languages do not support coproducts, and that makes you suffer. Here's what you have to write in Golang. That's code that programmers learn to write in Golang. They're told to write code like this. And you're doomed to write this because there's no other way in Golang to make it work. Essentially, you're performing an operation that can fail, and you return a pair of result and error, instead of returning a disjunction, which is either a result or an error. And that promotes many ways that encourages you sometimes to make a mistake that's hard to find. And there's nothing you can do to fix it. In Scala, you would return this type, and all of these errors would just disappear. They would be impossible to make. For example, to return both error and result, or imagine that your result type is the same as error type, and you mix them up. You return first error and then result, but you don't notice. That could happen. Or you forget to check, so you say error is not equal to nil, but actually you should have checked that it's equal to nil or something. The compiler will not help you checking this. So that's the kind of thing that happens if your programming language does not support coproducts or disjunctive types. So far, I've been talking about high-level things I learned, about functional programming as a paradigm, but there were also many specific things, details that I was surprised to learn. As I was working on each chapter, I formulated and proved every statement that I wanted to make, that this is a functor, that is a monad, and so on. And when you do that, sometimes your calculations and derivations give you a result that you did not expect. And indeed, each chapter gave me at least one surprising realization. Sometimes what I believed I tried to prove, but I could not prove it, and it turned out to be incorrect. Or something that I did not expect turned out to be true and I could prove it. From the first 3 chapters, one realization was that nameless functions are actually used widely in mathematics, but they're just not shown explicitly in the notation, they're hidden. For example, this is the mathematical notation for computing the sum of the squares of the first 100 numbers, integers, and this notation doesn't seem to contain any nameless functions, but if you write the code in Scala, the code would look like this, and you see there is a nameless function inside which introduces the variable n as a bound variable, and the mathematical notation introduces the variable n as a bound variable exactly in the same way, just in a different notation that doesn't emphasize that there is a function inside. Similarly, with integration, there's a different notation with this d symbol, which introduces the bound variable x. And this is the variable x that is used inside. And when you implement numerical integration, the API could look like this, where you would have an explicit nameless function as an argument. And mathematical usage actually has the same rules about variables, for instance, that variables are immutable. So for example, this x here cannot be modified inside this expression, or that variables inside the scope of a function will shadow any other variable defined outside with the same name. And this is exactly the same as the usage of variables in mathematics. So I realized that these rules that one learns in functional programming of lexical scoping and shadowing of variables and so on, they just come straight from mathematics. They are the same rules that mathematicians developed. And that's a good thing, because mathematics has thousands of years of experience working with data of different kinds. And so this notation and these rules are very productive. They help avoid mistakes, and that's what functional programming uses. As I was coding up different algorithms for data structures, I realized that a lot of those algorithms will be not tail recursive. So that is a problem of stack safety that needs to be addressed in some way, but I'm not addressing it in my book. It's an implementation detail that is very important. For example, even a map function for a tree data structure will have not a tail recursive code, as that I'm showing in my book. So there are ways of dealing with this, but I'm not going to talk about them in my book. I'm concerned with proving properties of these functions and how to implement them better. That's a separate important question. Another surprise for me was that there is a data structure that is called perfect shaped trees. So trees that have exactly the same branching at every point, and they have exactly the same depth at every point. So for instance, a perfect shaped binary tree, it looks like this at depth 3. it was not something I expected, that you can actually define a type that will describe precisely those trees and no others. So that will exclude the possibility that you do not branch here, for instance, that you have here A5, A6, but here only A7 in this place. So you could exclude this by defining a type, so it will not compile unless you have the right number of data items in your tree. And that was a surprise to me, that you can actually do that. In chapters 4 and 5, mostly I was concerned with understanding function types and how to derive types from code. That is what one calls type inference in functional programming. You have a piece of code and you determine a general type signature of that code. What I realized is that there is symmetrically code inference, determining code from type. So if you're given a type signature of a function, in many cases, you can determine its code. And there's an algorithm for that, which I implemented in a library called Curry-Howard. And this is a practical application of the theory that is called the Curry-Howard isomorphism. So this theory explains in what cases you can implement a function given its type signature. Here are some examples running code using that library. So this library defines a macro called implement that examines the type signature on the left and generates the code for it immediately and compiles it. So for example, this function in takes a value of type A, a value of type option B, and returns a value of type option of pair AB. Now the only way this can go is when B is an empty option, and you have to return empty option because there is no B that you could return in there. And if B is a non-empty option, then you can put an A inside that option. So this code is reasonably unique. Of course, there's another possibility where you always return none in this function, but this is not interesting and this loses information, and so this is certainly not what you want in this kind of type signature. So the library assumes that this is not what you want, and it will not generate such code if there is a better option. So the better option will be realized automatically. So now after you type this in, the function in is available and you can just use it. So for instance, on some types, since it's working on any types A and B, you see that this is what you expect. Here is a more complicated example of a type signature. This is artificial, just to show you that type signatures could be quite complicated, and it's far from obvious that you can implement a function with this type signature. But the algorithm goes through this type signature and finds the implementation. And so there's a facility to print the code that is generated. And this is the code. So these are some complicated and nested nameless functions. Note that in this example, it's almost the same type signature as this one, except I changed here A to B. And for some reason now, this type signature cannot be implemented. So there is no code that implements this type signature, and the algorithm proves that. And so you have a compilation error, you have a type error in this, in some sense. This type has no implementations. So this is what my surprise was, that you could actually implement this automatically, and you can derive code from types in many cases, certainly not in every case. From the chapters 6 to 8, they talk about functors and type classes. One of the surprising things I found is that subtypes and supertypes do not correspond to supersets or subsets. So if A is a subtype of B, it is not always the same that values of type A are a superset of values of type B, or a subset of values of type B. It is neither that nor this in general. So there are examples where you have a superset, there are examples where you have a subset, and there are examples that are neither. So that's quite surprising. Sometimes you see statements that subtype is a subset or a superset or something like that, but this is not always true. Another major discovery that I've made was that if you have functions that operate on disjunctive types or algebraic data types with disjunction in them, so some kind of either or case classes with several cases, then it is useful to write their code in a matrix form. And this matrix notation is quite useful for proofs, for symbolic derivations. It is certainly not something you want to write in your editor, but it is quite useful for symbolic derivation. So here's an example. If you have a function that takes either a, b, returns either c, d, and the code is a pattern match of some kind, then you can write this as a matrix in this form. You annotate the types of each part of the disjunction on the input and on the output. And then in this matrix, in each row, you will only fill one place, because there's only one part of the disjunction that you can return. So for example, if you return the right one, that means you return here. And then you write this function that takes x and returns f of x in this place in the matrix. And similarly, for the second line in the case match expression, you write here in the second row of the matrix this function from y to g of y. Y needs to have type b, and g of y needs to have type c. So that when you write this code, the code doesn't tell you what types you have. Instead, it gives you names of the case classes. The matrix notation doesn't give you any names of case classes, but it gives you the types that you are taking in and outputting. And that is much more useful when you do symbolic derivations. So this matrix notation is used throughout my book for proofs of all kinds of statements, properties, for functions that have to operate on disjunctive types. Another thing I found is that type classes can be viewed as partial functions from types to values. So it's a function from type to value. It means it's a value parameterized by type, but this type is not allowed to be any type. It must be a specific set of types for which a type class instance is available. And so it's a partial function. It's not a total function from type to value. But this is a partial function that's safe to use, because if you use it incorrectly, if you use it on a type that doesn't have the type class instance, that's a compile time error. So because it's a function from type to values, the types are checked at compile time, and so partial functions are okay to use in this case. So this is a useful way of looking at type classes. How you implement this partial function, there can be different ways of implementing it, but that's what you want to implement. You want to say which types are allowed as arguments or as type parameters for this function. Finally, I realized that monoids are everywhere. Every non-parameterized type has a monoid structure: integer, string, boolean, character, array of integer, or anything of that kind. Any data structure basically applied to any specific type, a tree of strings, all of that has a monoid structure. So you can define a monoid instance for every specific type. The only thing you cannot define a monoid instance for is a type parameter A. You have no idea what that is, and you don't know how to define a monoid for it. So, so if you don't have parameterized types, if you don't have type parameters, then you can define a monoid structure. That's a kind of an interesting observation. Chapters 9 to 12 talk about type classes such as filterable, monad, applicative, and traversable. And so filterable functors is a type class that is not often discussed. It is kind of a neglected type class, but it's a useful type class with interesting and useful properties. So I devoted a long chapter to it. It's a little easier than monads, and it prepares you for understanding monads. I discovered that types like these are not monads, so they cannot be monads. You cannot define correct methods for them, which is surprising. Very simple type. Option A is a monad. Option pair AA is not. It's applicative, it's traversable, it's filterable, it's a functor, but it's not a monad. It's a very surprising thing. Nobody really knows why, so how to explain that it's not a monad. You just try to define it and you fail to satisfy the laws. While studying monads in depth, I found that essentially we always use some kind of runners with monads to extract values from a monad. And some monads have interesting runners, but some monads don't. And so, for example, the state monad has a runner that does not obey a certain law. Monads need to, it obeys the laws of monad, but the runner for it does not obey the laws of monad morphisms. And this is strange, but this tells you that the state monad needs to be used with care. If you have a state monad anywhere and you run that program, you have to run the entire state monad program at once. You cannot run it in parts and combine the parts. Continuation monad doesn't seem to have any reasonable runner. It's a difficult monad. It has difficult properties, and so it's interesting that I was able to find specific violations of laws with certain runners. Another realization for me that was surprising is that one often hears things like flat map is equivalent to map and flatten. They're not equivalent, actually. You have to assume certain laws before you can prove equivalence. It's not enough to just say that flatten is the same as equal to flat map of identity, and flat map of f is equal to map f dot flatten. Now it's equal, but it does not mean that you have equivalence. You need to prove isomorphism. You need to say that you start with flatten, you define flat map from it. So you started here. You define a flat map through flatten by this equation. Then you define another flatten through that flat map by this equation. And you must show that this flatten is the same as the one you started with. And vice versa. You begin with flat map, you define flatten from it, and then you define a new flat map using that flatten. And then you have to show that this new flat map is the same as the one you started with over there. And that's not obvious. You have to prove this. And when you try to prove this, you find that you cannot prove this. It's just not true. But what you can prove is that if you assume additionally a naturality law for flat map, then you can prove that this is isomorphic. So actually it is not true that they're equivalent. Only flat map with a naturality law, with a specific naturality law, it has two different laws, but you need one of them. Only that is equivalent to map with flatten. And I discovered that almost every situation where you have equivalent methods in type classes, there is some kind of naturality law required. Now, it's not a big deal. Naturality laws are pretty much always satisfied. But unless you realize this, the statement like this that flat map is equivalent to map with flattened can be confusing. You get a feeling that something is wrong here. You cannot just have one function equivalent to two functions. What does it even mean? So anyway, I have now a specific, very clear and rigorous formulation of this with proofs. So another thing I found is that almost all monads are non-commutative, but almost all applicative functors are commutative. So the fact that all monads are applicative is not very useful. The applicative functors we want to use are pretty much all commutative, and the applicative functors that come from monads are not going to be commutative. So that applicative functors have to be defined separately, even though the same type constructor is a monad. The automatic definition of applicative functions like zip and app from monad is almost never useful. That's something I found. Another surprise is that all contravariant functors are applicative. If these contravariant functors are defined using the 6 standard type constructions that I showed before, then it's applicative. All of them. It's very interesting that there aren't any other contravariant functors than applicative. And finally, I was surprised to see that you can define breadth-first traversal of trees using fold and traverse. So you can define a special version of traverse that will perform breadth-first traversal. Not only depth-first traversal, which is the standard way that it's defined, but you can also define breadth-first traversal. I thought it was impossible. When I first thought about it, I thought it's impossible. I'm going to show that it's impossible. But I couldn't show that it's impossible. And then I realized that I can actually implement it. So in the book now, I will show the code for traverse doing a breadth-first traversal for trees. That's a kind of not very easy, but possible. In chapter 13, I'm talking about free type class constructions like free functor, free filterable, free applicative, free monad, and so on. So one thing I realized when looking at this is that not all type classes have a free construction. For example, there is no free foldable or free traversable. There are only certain type classes that allow you to do a free construction. And that is kind of interesting. So another thing I found is that the so-called tagless final, it's a design pattern that recently became popular, is equivalent to the free monad. It's just a different code that does the same thing in a slightly different type, slightly different way, but it's equivalent. So if you can do something with a free monad, you can also do this with tagless final and vice versa. So a joke that you can do about this is that tagless final is just the church encoding of the free monad. What is the problem? The problem is the church encoding. Well, first of all, the free monad is far from obvious what that is. And the church encoding is a very difficult thing to reason about. I thought I would just give a proof that this equivalence holds. And I spent several months trying to prove that. It's a very hard thing to prove. My book has a proof, but it uses a lot of difficult theory, relational parametricity. I'm also using some talk slides that I found that don't seem to be published as a paper. So all of that seems to be necessary to prove that the church encoding actually works the way we want to. The good thing, of course, is that programmers do not need to study these proofs. I wanted to write them because I wanted to know that the statement is correct. But now that we know this, we don't have to study these proofs. We need to know how to use the church encoding, how to write code correctly. That we need to learn, but that's a lot easier. You just look at examples, you kind of see how to do it. You need to know that there is a proof and that there is actually a correct formulation, which is rigorous. And finally, the chapter on monad transformers The longest chapter, twice as long as most other chapters. Very difficult technical subject with a lot of detail and a lot of surprises for me. So one surprise is that nobody really knows how to define a monad transformer for a monad that you might get. So imagine there are lots of monads, and suppose you need a transformer for it. There is no method that would generally work for any monad to define its transformer. Although, for every specific monad that we can define, there is a transformer. Nobody knows a counterexample, a monad that doesn't have a transformer. For a long time, I thought I had a counterexample. I thought I had a monad that didn't have a transformer, but that turned out to be incorrect. I found a transformer for that too. So when I formulated all the laws of monad transformers, then I found that from category theory you can have a joke like this. Monad transformers are just pointed endofunctors in the category of monads. What is the problem? Now the problem is, first of all, the category of monads is a difficult thing to work with because it's functions, the morphisms in this category are functions that have to be monad morphisms, that have to satisfy certain complicated laws that you have to check every time. Endofunctors in this category is a very complicated set of objects with a lot of laws that you have to verify every time. Pointed endofunctors, that's another set of laws. So in total, there are 18 laws behind this one line. Okay, so this is far from clear, far from obvious. If somebody tells you this, they're making a joke. It's not obvious. It's not easy. There are 18 laws if you just write down what this means. And finally, I found to my dismay that some monad transformers are incomplete and actually unusable. Especially the continuation monad and the codensity monad have transformers that are unusable. They do not have certain methods that are necessary if you wanted to use transformers in practice. To use transformers in practice means you have a couple of monads or 3 or 4 different monads, and you want to combine them into one big monad, and you want to lift operations from each of those monads to the big monad. So if you have, say, some computation that gives you a continuation monad value, then this continuation monad value needs to be lifted to the big monad. But you cannot do that. There's no lift function that corresponds to that lifting. You can lift other monads, but not continuation into the big monad. And the same as for codensity. So these monads are unusable in general. So you can use them in certain specific cases, in certain limited ways, but it is not possible to combine arbitrary computations in these monads with arbitrary computations with other monads. So this concludes my talk. Functional programming has a steep learning curve with a lot of material that took me several years to learn and to write up in an understandable, rigorous way. However, programmers already benefit from the simplest techniques of functional programming, mostly map, filter, fold, algebraic data types, for yield in Scala. That gives you so many benefits for relatively little learning that most programmers use that and not much more from functional programming. But there is a lot more for which the full derivations from the beginning took about 800 pages in the book. The difficulty of these derivations, I would compare them to undergraduate calculus or algebra. So some of these calculations are long, but they're not difficult in the sense of complicated abstract notions that you have to deal with. They're difficult, like a long formula is difficult. You have to not forget any part of it when you write it out and transform some part of the formula. You need to keep other parts unchanged and so on. And remember the rules of transformation. That's the same level of difficulty as undergraduate calculus, I would say. So certainly this is not PhD level mathematics. So these 800 pages certainly are not at PhD level. A lot of those calculations are just long, and they could have been even longer if I used, say, Scala or Haskell program syntax instead of my notation that I developed for the proofs. But even with that notation, it's a fair amount of derivation. Now, a lot of this derivation is just to make sure that the statements are correct. These derivations are not directly used for writing code. The results of these derivations are used. So you need to know which functors, which monads and so on can be used in a particular place in your code. The book proves that these monads and functors and so on are correct. You don't need to go through those proofs necessarily, but you can if you want to. That's one of the reasons I'm writing this book. And as I was describing, this theory is directly beneficial for coding. This theory is about writing code, is about what data structures you should use if you want a monad or a functor, or why would you want a functor, why would you want a monad. So knowing that this is based on rigorous derivation on mathematics makes programmers work closer to engineering. Where engineering designs are based on mathematical computation, the engineers themselves don't have to prove all the theorems as they work. They use the results of proofs. Just like programmers who use functional programming use the results of all these proofs, they do not have to do the proofs as they code. So that makes programmers work really a bit closer to engineering. The book is available on GitHub. It's a free book in the sense of the free documentation license. So you're allowed to copy it, you're allowed to print it,